Hello. So today I'm going to tell you about a way for achieving phase determinism and frame alignment using Xilinx transceivers for timing distribution systems. So I will start with an introduction for what is phase determinism and frame alignment, why we need it. Then I'll show you the proposed solution and measurements about this solution. And I will conclude with some theory about how to perform phase measurements inside the FPGA, and I will compare my solutions with other existing solutions. So let's start with some context. In the LHC, particles are accelerated thanks to the RF cavities situated in point 4. So these RF cavities produces an RF frequency, which gives to the bunches of particles their spacing. This radio frequency is 40 MHz, and the cavities also produce a clock, which is called the bunch clock, and this clock is 30 MHz and gives you the information about the rate of collision of particles. So this bunch clock produced in the cavities has to be distributed through traveling through fibers to the 4 experiments and to all the thousands of endpoints inside the detectors in order to synchronize the detector, the electronics for the data acquisition from the collisions. So because of the high luminosity upgrade, there will be an increase of the collisions per bunch crossing, and this will create a high pile-up effect, meaning that there will be many superposed collisions in the same bunch crossing, and so will be very difficult to distinguish those collisions. So 4D techniques means to add a fourth dimension, which is time, to be extremely precise in order to be able to distinguish those superposed collisions. So this is an example of a timing distribution system currently used in the Atlas network. The goal is to, let's say, we have the bunch clock represented by the first PLL entering in the backend, and then this bunch clock is embedded in the data stream and distributed through this cascade of FPGA until it reaches the radiation hard front end. And the goal here is to have a fixed phase relation between the data entering in the front end and the bunch clock entering in the back end. So to do so, each FPGA performs a clock recovery on the data stream, and the recovered clock is used as a reference for the next transmission. And in this way, the transmitted data is always in a fixed phase relation to the incoming data stream. So because of this, we need phase alignment, because in the FPGA we cannot enter with a gigabit clock signal, so we do a parallelization of the data stream in a bus, in our case of 30 bits. And so there is a frequency division from gigahertz to megahertz, and this means that we need to perform frame alignment, and frame alignment is done thanks to the presence of frame headers called commas in the data stream. And now I will show you how frame alignment works in the case of the receiver. So we have the data stream entering in the receiver. The first operation is the clock and data recovery, the CDR. This creates a fast recovered clock, which is gigahertz. And then we have the parallelization in the bus. So we need to divide our fast recovered clock to be a divided, slower recovered clock. And this creates our issue, because when we do this division, at each startup, the phase of our divided recovered clock will be 1 in the 40 possibilities. And the same way, the offset of the comma in the bus will be 1, there will be 30 possible offsets. And this creates our problem with phase determinism, because we have when we we start the link, we lose the phase reference from the divided recovered clock to our data stream. But then we have an alignment procedure in the receiver, and this procedure reads the position of the comma in the bus and shifts bit per bit until the comma reaches the predefined position. And in this way, also the phase of the recovered clock is shifted. And like that, we achieve phase determinism in the receiver. So now let's see what happens in the transmitter, which is the part we are interested in today. So we have a symmetric situation. This is our reference clock that has the phase we want to propagate through the transmission. And this could be, for example, the recovered clock from before, the slow one. So we need to provide this reference clock. This goes in a PLL, which creates a frequency multiplication, and we get our fast reference clock to clock the serializer. But from the other side, we need to divide it, and this becomes X clock to clock the serializer from the other side. So because of this frequency multiplication and frequency division, we completely lose the phase reference of the transmitted data from our reference clock. And as you can see, there is no alignment procedure in this system. So we need a solution for this. So this is the default clocking architecture provided by Xilinx. We can see the blue path is for the reference clock to become the source of our TX user clock, which is the clock we use to send the data to the transceiver. But then we have the clock, the frequency multiplication and division to create a X clock, and so we lose the determinism. So now I'll show you the proposed solution overlaid on this drawing. So we have the same path for our reference clock in blue, which still becomes TX user clock. But then there is a way to output from the transceiver a clock, X clock, from a port called TX out clock PCS. And the nice thing is that X clock has a fixed phase relation to the transmitted data. And whenever we start the system, X clock has always a fixed phase to the transmitted data, while it jumps from the phase of our reference and the TX user clock. But at this point, the idea is to perform a phase measurement between X clock and our reference TX user clock. And to do the phase measurement, we can use a DDMTD, and I will tell you later how this works. So the DDMTD gives us the phase between X clock and the user clock. And with this information, we can phase shift the phase of X clock to be matched with our reference. And in this way, we end up with a phase of the transmitted data fixed to the phase of our reference, also between startup. So we do this after startup, and then we always have the same phase. So how to do the phase shift? Xilinx transceivers provide a device called a phase interpolator. So this is a phase shifter that can be controlled from outside. And it has a step of 1 UI divided by 64. The UI is the duration of 1 bit in the fast stream. And so we just need to provide a control to the phase interpolator, which is an integer number of UIs. So integer number of 64 single shifts. And in this way, we achieve a perfect phase shift of exactly what we want. So this is what happens when we don't do anything. So between each point, there is a reset, and we can see that in green, we have the phase measured with the DDMTD between our TX reference and the X clock, and we see our 30 possible phases C paired by 1 UI, which in our case is 100 picoseconds. So this is our lack of determinism. In blue, which you don't see because it's below the green measurements, we have a scope measurement between our TX reference and the data. And you see that X clock and the data is the same phase. So let's see what happens when we apply this phase measurement and the phase shift technique to achieve the determinism. So in green, still we have the phase between the reference and X clock, and we see that after measuring and shifting, we end up with just one phase instead of 40 different phases. And the final determinism is below 2 picoseconds, so this is perfect for our goal for the high luminosity upgrade. So let's see at this point how phase measurement works inside the FPGA. So the device is called the digital dual mixer time difference, and it allows to achieve picosecond level accuracy, even femtosecond level accuracy inside FPGA. So we don't need extremely fast ways of having phase measurements because we do this only at startup, so it can take milliseconds, but in our case just microseconds is enough. A couple of microseconds is enough. So this system requires an offset clock to be provided, and this offset clock has to have a frequency which is very close but smaller to the input frequencies of the clock we want to do the phase measurements on. So we have a front end in this TD-MTD, which is the time critical part. And so this front end is made of 2 samplers, which samples the input clock with this slightly slower clock. And this means that we are scanning the input clock with this offset clock, and what we get in the output of the sampler is a period amplified clock which has the same phase of the input clock. And we can see here a time and frequency analysis of this concept. So we have the input clock, we convert it in frequency, we apply the transformations for the sampling and the holding, and then when we go back in time, we demonstrate that there is this amplification effect of the period. The amplification factor for our use case is 10 to 100,000. But because we are sampling this clock with a slightly slower clock, we will also sample jitter, and this creates glitches in the period amplified output. So we need a state machine to remove those glitches, and at the end we end up with this clean period amplified clock. So at this point it's easy because we have 2 period amplified clocks with the same phase of the original clocks, and so we can use a normal counter of the FPGA to count between the edges of those clocks. And yes, with these formulas we extract the phase from the counter value. Now, of course, there is metastability, jitter, noise. So we take a lot of measurements, then we do the average, and we end up with an extremely precise value with the accuracy of the picosecond. So let's see also, so I'm at the end of the presentation. Those are other techniques currently used to achieve these results. So let's start with the one which we don't use because it's not good enough. This is called the buffer bypass. It's shown in red. And the buffer bypass works by bypassing the FIFO, which is called the elastic buffer, and doing so, for some way, the situation improves by a lot. We kind of have phase determinism, but the range of the phase is 30 picoseconds. Then we should also look at what happens in other transceivers. This is a GTH transceiver that is a GTY. So this is not good enough for our target of picosecond level phase determinism. And so the currently used solution is the HPTD IP core, which has been developed by Eduardo Mendes. And this solution provides same result as mine, so less than 2 picosecond peak-to-peak of phase determinism. This works with the elastic buffer as my solution. And it works like this. So same concept of phase shifting with a phase interpolator, but instead of reading the phase between X clock and the user clock with a DDMTD, the idea is to read a status from the FIFO. The status is called the TXBuff status, and this gives you the information about how much field is this FIFO, if more than half or less than half field. And so the idea is to read this information, phase shift until the flag toggles. And when we reach this state, it means that we have a fixed offset between the reading pointer and the writing pointer of the FIFO. And so we achieve phase determinism. So let's see what changes between those solutions. My solution and the HPTD IP core provides the same phase determinism at the end, while the buffer bypass is not good enough. For resources, I need a DDMTD, and the HPTD need this final state machine for the alignment, which reads the flag and decides the shift. We both need a DRP controller, the dynamic reconfiguration port, to talk with the phase interpolator of the transceiver for the phase shift. And of course, we need this phase interpolator. Then I need access to this X clock, which is a clock that has the same phase of the transmitted data, while the HPTD IP core needs access to this TXBuff status flag. And maybe in future, this TXBuff status flag will not be available anymore, so it's good to have a second option. Also, let's say the phase interpolator will not be available anymore. Another way could be using the FIFO flag information or the DDMTD phase to know in which of the 30 possibility we end up, and then we can do a roulette approach and reset until we have the correct phase. So why have I developed this second option if we already have one that works? Well, for this reason, maybe in future will not be available anymore, but also because when I started investigating the HPTD IP core solution, I wasn't really able to understand properly how it works, really. I struggled a little to make it work. At the beginning, I had like 10 picoseconds of determinism, not true. Then I managed to make it work, but at the same time, I wanted to try other ways to see if the concept really can work, and it can. And yes, so now we have 2 solutions. And if you are interested to play with mine, it's here. You can take this example project and see it running. Thank you.
Thank you, Eduardo. We have time for a couple of questions. We're running a bit late, so...
Hi, very nice presentation. You described how you have your RX inputs then synchronized to your TX.
Yes.
Is that through the FRAC-XO or external jitter attenuator? And then how does that then interact with then this further determinism?
Can you repeat?
Sorry. You have the TX and RX synchronized.
Yes.
So that's the first step.
Yes.
So I guess I'm asking, how is that synchronized? Is it through a jitter attenuator or the FRAC-XO?
Yes. Okay. Yes. Let's say between. Okay, so when I do the clock recovery and I use the recovered clock as a reference, if this is what you mean?
Yes, but
Yes.
so therefore, do you clean up the recovered clock using?
Yes, there is a jitter cleaner. So the recovered clock goes in a jitter cleaner, and the output of the jitter cleaner is our reference for the transmission. And this jitter cleaner, to maintain phase determinism, is in zero delay mode. So it's a Skyworks PLL, which has this zero delay mode, which guarantees fixed latency between input and output.
Okay. And are you aware of the FRAC-XO method, which was developed by CERN?
Of the, sorry?
The FRAC-XO.
No.
It's a module that Xilinx provides.
Okay.
It uses the SDM ports, which I'm not sure if that's the same ports that you're using. So I'm going to go back and look at the transceiver just to sort of see whether the two methods are compatible or they're using the same port set, for example. So,
I don't know about this method.
okay.
Thank you.
Thank you.
Yes.
Quick question. How do you generate the helper frequency for the DNTD?
So the helper PLL, the Skyworks PLL we use as a jitter cleaner, has the possibility also to create this frequency. Okay. So we just program it with the clock builder, and it's compatible. So yes.
Okay, last question here, and then we move forward.
Hello, that's very interesting what you are talking about. I have a question concerning slides 11 and 21. Then you are showing a slow reference clock, which I was really not aware of. I thought that all this structure was doing like this, that the reference clock was coming to a PLL, generating the TX ref clock, and then all of that was synchronized with this clock, not something like going aside with a slow reference, which will then create a complete unsynchronization. I actually was implementing this always actually without this FIFO elastic buffer, and there was never any problem. It was like this, that whatever you write with a TX clock, a TX user clock, is synchronous with the serializer. So there was never any problem I have observed. I am quite astonished that there is some slow reference clock which is here around. I don't know where is it coming from.
So this slow reference goes also in a PLL, but the frequency doesn't change, so the phase doesn't change. But to generate our clock to sample the serializer, we need to multiply. No, because this goes out at gigahertz. So that is why we lose the determinism. So if you say you don't lose the determinism,
No, I have never observed any problem with the synchronization. So always it was like this, but whatever you are writing to the TX buffer, parallel buffer, it goes synchronous out, and there's always synchronized to the TX user clock.
So, I mean, it's synchronous, but at the level of UI, not at the level of frames. So maybe that's the thing?
This is synchronized at the level of frames, of course, and also at the level of bits. But maybe I'm wrong. Maybe I'm not, something maybe. I have missed something.
Yes, thank you.
Let's invite to continue offline this discussion.
Yes.
Let's thank the speaker again. Thank you, Eduardo.